Hi everyone. In this video, we are going to be talking about integration by parts for Math 1452 at Texas Tech University, which is Calculus 2. So integration by parts is one of the integration methods that we learn in this course in Chapter 7. So integration by parts is going to be the integral rule that lets us undo the derivative rule that's the product rule. So we've seen something like this before. You may remember that U substitution is what lets us undo the chain rule for derivatives. And likewise, integration by parts is going to let us undo the product rule for derivatives. So just to briefly illustrate what I mean by that if we have functions u and v with continuous derivatives, well, that means they're differentiable, so we can take the derivative of their product. So to do this, we use the product rule as normal. So we take the derivative of the first times the second plus the derivative of the second times the first. So this is just the product rule. And so we can integrate each of these three terms. And from the second fundamental theorem of calculus, we know that these derivatives and integrals are going to cancel out. And by rearranging this, simplifying and rearranging this equality is what's going to give us this equality here, which is the integration by parts formula. So what integration by parts does is if we have an integral u times dv, then instead of integrating that integral, we rewrite this using this equation to be the product of uv minus a new integral where our new integrand is v du. So if we have an integrand that's too hard for us to deal with, we can translate it into an integrand that's hopefully easier to deal with. So this method relies on identifying our integrand and breaking it into two parts, a u and a dv. And that u, whenever we translate to our new integral, is going to translate to du. So just to draw that, our u becomes du and our dv becomes v. So that means that whenever we're identifying u, it needs to be something easily differentiable so that we can now have du. And for dv, it needs to be something easily integrable because it translates into v. So to identify u and v, there's a hierarchy we can use that is in the form of an acronym LIPET, L-I-P-E-T. So let's go through what these mean. They're all different types of functions that we see that we have commonly been differentiating and integrating. So the L stands for logarithm. The I stands for inverse trig. The P stands for polynomial. The E stands for exponential. And the T stands for just a normal trig function. So these kind of go in order, where these top ones are hard to integrate. And then as we go down, these are easy to integrate. Because remember, our dv needs to be integrated to transform into v. So the things that are hard to integrate, we're going to put as our u. So these 5 letters are going to correspond with what we say that our value is for u. So whenever we're looking at our integrand, we're going to identify the pieces of it and what types of functions they are. And then we go down the list and check if our integrand has that type of function. If it does, we set that function to be u, and the rest of the integrand, including the dx, becomes dv. So let's look at some examples. So our first integral is the integral of x times e to the x. So that x that's highlighted in yellow is a polynomial function, and that e to the x that's highlighted in orange is an exponential function. So we can see that polynomial comes before exponential in our acronym LIPET. So that means that our u is going to be our x because it's a polynomial, and our dv is going to be everything else. So if I cross off that x, everything else is going to be e to the x and the dx, and that's our exponential, which I will abbreviate dx. Okay, our next example is the integral of x squared ln of x. So x squared, highlighted in yellow, is a polynomial function, and the ln of x, highlighted in blue, is a logarithm. So L comes before P and lip it. So that means that our u is going to be the ln of x, and our dv, again, is everything else. So that's going to be x squared dx. And so these are logarithms and polynomials. So you can see just on these first two examples that polynomials being in the middle will often be u and dv, just depending on which question we're looking at. The next one we have is the integral of arc sine of x dx. So our only term in our integrand here is the arc sine, which is inverse trig. So because that's the only thing, we are just going to put u as arc sine of x, and then everything else, which now is just dx, becomes our dv. So our u was our inverse trig, but dv did not have any function associated with it. And lastly, we're integrating x times sine of x. So x, highlighted in yellow, is a polynomial, and sine, highlighted in pink, is trig. And because p comes before t, our x is our u, and everything else is dv. So that's sine of x dx. So this is our polynomial, and this is our trig. Okay, so all of these have to deal with, once we know we're using integration by parts, how can we identify our u and our dv? So there's actually going to be 3 different types of integration by parts once we proceed. And it all has to do with what our new integral looks like. So remember, we are changing our integral from our integrand being u dv to our integrand being v du. And hopefully that v du is simpler than our original integrand u dv. So depending on how we can integrate that v du, we have 3 different types of integration by parts. So the first one is basic integration by parts. And in this one, we can use anti-differentiation on the integral v du. So that means the integral that we come up with now is simple enough that we can just integrate it simply. The next kind of integration by parts is repeated. So this means that we need to repeat and use integration by parts again. So we're going to use integration by parts on this integral v du. So we needed to use it on our original, but then we rewrote an integral that again needs integration by parts. And lastly is circular. So for this one, we are again going to use integration by parts on the integral of v du, but we're actually going to circle back to the original integral. U dv. So when we repeat that integration by parts, we actually get back to our original integral, and then we have to do some algebra. So this is kind of an overview of what integration by parts is. So in this video, we will finish by working an example of the basic integration by parts. So we're going to evaluate that last integral we looked at, the integral of x sine of x using integration by parts. So as we identified up above, our u is x and our du is sine of x dx. So we need to change our u into du, and we do that by taking a derivative. So the integral of x, the derivative of x is 1, and then that was with respect to x. And then we integrate dv to try and get back to v. So we are integrating sine of x dx, and the integral of sine is going to be negative cosine. And so you'll notice that whenever we're doing this, we're not going to worry about putting a plus c on anything, just because we'll do that as our last step. So we have differentiated u, and integrated dv to now have our new v and du. So now we just put everything into the integration by parts formula. So the integral of u dv, which was the integral of x sine of x dx, can be rewritten as u times v, which is negative x times cosine of x, minus the integral of v du. So this is minus cosine of x dx. So the first thing I'm going to do is I'm going to rewrite that double negative as a positive. So my uv stays the same, and then I add the integral of cosine of x dx. And now I just integrate cosine. So this was their first case, basic integration by parts, because our new integral is just the integral of cosine, which is one of our anti-differentiation rules. So this is going to be the integral of cosine is positive sine. And now that we integrate here, as our last step, we add our plus c. So this is how we use that basic integration by parts. So we use our acronym LIPIT to identify u and v, take a derivative of u, integrate dv, and then rewrite and simplify. So this is where we will finish this video. In the next video, we will do examples of repeated and circular integration by parts.